Hey guys, welcome to ANS Solver. Today we'll be doing the concept of the normal distribution as an approximation to the Poisson distribution, basically converting Poisson distribution to normal distribution, and this is a subtopic in the chapter of Poisson distribution. So first, let's start with the condition, okay? Because even in the previous video when we were converting from binomial to Poisson, okay, we had condition. Here also we have condition. Okay, so basically the most important condition here, okay, is that your lambda which you have, okay, is more than 15. Okay, if your lambda is more than 15, only then you can convert from Poisson to normal. Okay, so that's the main condition. Now let's come to distribution conversion. That basically means if I have, let's say, x with a Poisson distribution which looks something like this. When we convert this Poisson distribution, okay, where my lambda is more than 15, when I convert this to normal, it will basically, become something like this. Normal with a lambda, comma lambda. Why is it something like this? Because I know the lambda here is the mean and the variance, correct? And in my normal distribution, we always write mean comma variance, correct? In the normal distribution, we always write mean comma variance, correct? So that's why your distribution will basically be converted to lambda comma lambda. Okay, this is very important to understand. Okay, now we have the continuity correction. This is a very important concept, okay, to understand. Okay, so now first, let's come to discrete variables and continuous variables. Okay, basically the Poisson distribution which you have, okay, the Poisson distribution and the binomial distribution, okay, are both discrete variables. But continuous variables is basically something like normal distribution, correct? So basically, when you are converting from discrete to discrete, you don't need the continuity correction. But if you are converting from, let's say, Poisson to normal, which is in this case, you need something called as the continuity correction. Or when you are converting from binomial to normal, that time you need the continuity correction. Binomial to normal we've done in AS level. Now we learn, we are learning Poisson to normal. Okay, because whenever you convert from a discrete variable to a continuous variable, there's always a continuity correction. So you can just remember it as whenever converting discrete to continuous, okay, a continuity correction, which is a CC, is required, correct? This is very important to understand because in some cases people forget the continuity correction. And now the continuity correction always has a value of 0.5. Now whether you add it to the value or subtract it to the value depends on the sign. Let's say if the sign I have is more than, if the sign is more than, then I add 0.5, correct? If the sign is more than equal to, then I subtract 0.5. If the sign is, let's say, less than, then I subtract 0.5. But if it's less than equal to, I add 0.5 to the value which I have, correct? This is really important to remember, even these signs, okay, because this is not given in your formula booklet, and it's better to remember these because sometimes it trick you, okay, in questions where you need to use the continuity correction and you need to know whether you need to add 0.5 or subtract 0.5, which is dependent on the sign. Okay, so basically this was basically the concept which you need to know. Now let's do some past paper examples so that we know how to implement this concept. So this example is basically from 2018 Feb-March paper 72. Okay, so the number of phone calls arriving in a 10-minute period, okay, at a switchboard is modeled by random variable x, which has a distribution of Poisson with a lambda of 4.1. Use an approximating distribution to find the probability that more than 90 calls, okay, are made in a 4-hour period. So basically I write time here and I write lambda here. I know in a 10-minute period, this is in minutes, you always need to see the unit. The lambda which I have is 4.1. Okay, but here you see there's a 4-hour period. So first you need to convert hours to minutes. I know 4 hours is 240 minutes. So I simply write 240 here. Correct? So the lambda in 240 minutes will basically be 4.1 divided by 10 multiplied by 240. Correct? Which is simply 98.4. So my new lambda is basically 98.4. Now you need to use an approximating distribution. Okay, so 98.4, I know if my lambda is more than 15, correct? I convert it basically to normal, correct? So basically I know in this case my 98.4 is more than 15. That means a suitable approximation will be basically a normal distribution. So I can write this as normal, and I know in the normal distribution it's always lambda comma lambda. So I write 98.4 comma 98.4. So now we are dealing with the normal distribution. So now it's basic. We basically need more than 90 calls. So I need the probability of x to be more than 90. Correct? So what I can do is I can basically make the normal distribution curve here. Correct? So here basically the lambda is basically the mean which I have here as 98.4, and here the value which I have is 90, which I know will lie less than the mean, let's say somewhere here. Okay, so 98.4 is the value here and 90 lies somewhere here. Basically the value lies somewhere here. Now I need more than this value, so I basically need the area here which I have shaded. Correct? This is what I need. So now in normal distribution we calculate the z value always. You need to recall this from AS level. Correct? Which is basically the value minus, it's always the mean, okay, over the standard deviation. Correct? You have basically the standard deviation. That's the formula which we learned in AS. But in this case, okay, my mean is my lambda. Correct? So I'll replace this with the lambda here. Correct? And the standard deviation which I have is the square root of lambda. Correct? This is what we had done. So basically lambda and root lambda. Correct? So now to calculate the z value, what I need is first my x value. My x value, is it 90? No. The most important step is basically the continuity correction. Okay, because you're converting from Poisson to normal, you need to know the continuity correction. Here in this case, I have a more than. Correct? That means I have 90, and because of the more than, I add 0.5. So I basically add 0.5 to the value which I have. So I can basically write this as 90.5, because you need to remember this table. For more than it's plus 0.5, less than it's minus 0.5, more than equal to is minus 0.5, and less than equal to is plus 0.5. Correct? So now basically my x will not be 90, it will be 90.5 minus, I'll have 98.4 divided by, I'll have the root of 98.4. Correct? So now I can basically solve this on the calci and get my z value, which in this case is minus 0.79 63. Correct? This is what I get my Z value as. Now, what do I need? I need more than the Z value, correct? So I know you need to know basically from AS level that phi is when you are calculating the less than, okay, less than or less than equal to, correct? And 1 minus the phi is when you're calculating the more than. Correct? This is what you basically have. So in this case, we are calculating the more than, so I write 1 minus the phi of minus 0.7963. Correct? Now, how do I calculate something like this? You need to know the calci method. So basically, on the calculator, what you need to do is you need to click on mode. When you click on mode, you need to click on 3 where stat is written. Correct? Then you need to click on AC. Then you need to click on shift. Correct? After shift, you need to click on 1. Correct? And then you need to click on 5. Okay, if this is the first time you're doing this, I know there are many buttons, okay, to press, but you need to remember this because this is the way how to calculate it. Correct? So on the display, you'll basically get 4 options, which is 1P, 2Q, 3R, and 4T. Correct? So options 2 and 4 are not that important. You need to know options 1 and 3. Option 1 is basically for the values which is less than or less than equal to. It doesn't matter because it's continuous. So the less than or less than equal to doesn't really matter when you're calculating it. It only matters during the continuity correction because the sign is important for that. Correct? So for basically less than values, you click on 1 and you click on R for more than values. Correct? This is what you need to know. This is continuous. Correct? So in this case, what are you calculating simply? You're calculating more than. So I click on option 3. Correct? So when I click on option 3, okay, on the display, you'll basically get R with a bracket. Correct? Now you basically put the value, which is minus 0.7963. You input this and you simply click on equal to. So you get your answer as 0.7871, which you can simply write to 3 significant figures as 0.787, which is basically your final answer. So through this question, you saw how many different steps you need to, take into account while solving this sum. This is a very important type of sum. First, you need to identify that a normal distribution has to be used with the condition that the lambda is more than 15. Correct? Then you need to use the formula z equals to x minus lambda over root of lambda. Okay, even this is important. I'll just, square this so that you're 100% sure, because you need to know that your mean and basically your mean is lambda and your standard deviation is root lambda. Correct? Then you need to take into account the most important thing, which is continuity correction, which will depend, on the sign which you have. You calculate your z value, then you use your calci. For all less than or less than equal to, you use 1. For more than equal to, you use 3. Correct? The option 3 here, which is basically P for less than. Remember it like this. P is always for less than. Okay? And R is for more than, because it's continuous. If it's more than or more than equal to or less than equal to, doesn't matter. It only matters for the continuity correction. For the continuity correction, it's really important. Okay, the sign. That's why I'm stressing on it, because many students go wrong, or sometimes they tend to forget that a continuity correction applies. Okay, so again, stressing over the point that a continuity correction basically applies when you're converting from discrete to continuous. Okay, always. Now let's do another last past paper example. So what you can do is, to test yourselves, you can pause the video and try to do it. If not, you can refer this, and later when you're doing the past paper questions, you can try it, the topic wise questions. And later also, if you're getting stuck, you can refer our video solutions which we've made for every topic wise and past paper video. Okay, so yeah, so basically this is from 2018 May June paper 71. So the number of e-readers sold in a 10-day period, okay, is modeled by the distribution Poisson with a lambda of 5.1. We need to use an approximation or approximating distribution to find the probability that fewer than 140 e-readers are sold in a 300-day period. So first the unit interval, I write days, I write lambda. I know for 10 days, the lambda which I have is 5.1. Here, I have a 300-day period. So I write 300 here, which is basically the lambda will be 5.1 over 10 into 300. Correct? So I can basically get my answer as 153. Now I know that my lambda is basically 153. So now I need to recall, okay, the distribution basically from Poisson to normal. The condition was that the lambda should be more than 15. In this case, I know my 153 is more than 15. So this can basically be converted to normal. So I can convert this from Poisson of 153 to the normal, where I simply write 153, 153. Correct? This is x distributed as. Correct? So now we are basically following the normal distribution. Correct? So you always need to remember the conditions thoroughly. Okay, it's a very important thing. Okay, so now what do I need? I need to calculate the probability that fewer than 140 readers. So I need the probability that x is fewer, which means strictly less than 140. So I can simply make my normal distribution curve. Correct? So now what I can simply do is, I can simply state that my lambda is 153, correct, which is basically the mean, because in normal it's always mean comma variance, and I know the value which I have 140 is lying somewhere here. Okay, it's basically the value, because continuity correction will also be there. Now I need fewer than this value. That means I need the value here. Correct? So basically I know my z is equal to, because this is Poisson to normal, I basically get x minus the mean, in this case it's lambda, divided by the root of lambda, which is the standard deviation. Now, a very important thing, because you're converting from discrete to continuous, you have the continuity correction. Correct? Here, you basically have a less than. A less than is basically a negative 0.5. In the previous example, we had a more than, that's why it was positive 0.5. But here we have negative 0.5. So we simply write this as 140 minus 0.5, where we simply get 139.5, which is my new value. So I write my z basically as 139.5 minus the lambda, which is 153, divided by the square root of the lambda, which is 153. So I get my z value basically as negative 1.0914. Correct? So now basically I need less than this value. So for less it's phi. So I simply write I need the phi of the z value, which is minus 1.0914. And another thing which I wanted to mention, which you must have noticed, that if you have a value which is less than the mean, the z value you will get is always negative. And if you get a value which is more than the mean, the z value will be positive. Okay, correct? This you might be knowing. So now the steps on the calci, which is important, I'll write it again, because these steps are really important. Correct? So on the calci, you simply need to click on mode. When you click on mode, you need to click on 3 where stat is written. Once you click on 3, you need to click on AC, then on shift. Once you click on shift, you click on 1, and then you click on 5. correct? So on your display, you basically get 1p, 2q, 3r, and 4t. Options 2 and 4 are not that important. You know option 1 is for the less than values and option 3 is for more than values. Correct? You only need to know whether it's less than equal to, more than equal to. Okay? So basically in this case you have a less than. So you click basically on option 1. Correct? So when you click on option 1, you basically get P with a bracket. In the bracket, you simply put the Z value which you get, which is minus 1.0914. Correct? When you input this and then click on equal to, you get your answer basically as 0.138. So basically your 0.138 is your final answer. Correct? So did you understand this problem? This was quite simple. Okay, so I showed you two different cases, one with a less than sign, one with a more than sign. Correct? The more than sign we did previously in the previous example. Okay, so I hope you have understood the conditions. The most important thing is, understanding the conditions, understanding the continuity correction, and remembering that you need to use a continuity correction while converting from Poisson to normal. Okay? When you're converting from Poisson to binomial, you don't need the continuity correction. Okay, you need to know that because it's within the discrete variables. Okay, so I know we've come to the end of the Poisson distribution chapter, but only knowing the concept won't help. Okay, you need a lot of practice. Okay, especially in stats, because there are different kind of languages, different type of questions which they ask in past papers. So you can practice the topic wise past paper so that you're thorough with this. Okay, and you understand how to solve the past paper questions. And even if you get stuck, we have provided video solutions so you can have a good look and master the chapter entirely. So thank you very much for watching the video and understanding the full chapter.